In this video, I will talk about Introduction to Higher Mathematics, which talks about proofs and definitions. It's Introduction to Mathematics and a little taste of number theory. So first we'll start off with definitions. Definition 1. An integer n is even if n is equal to 2k for some integer k. What this means is n is even if it can be written as 2 times some integer k. An example would be 10. 10 is even, and it can be written as 2 times 5. Or the number 12 is even because it can be written as 2 times 6. So it's even, a number is even if it can be written as 2 times some other number, some integer k. Definition 2. An integer n is odd if n is equal to 2k plus 1 for some integer k. This means a number is odd if it can be written as 2k plus 1. So an example would be 11. 11 is odd because it can be written as 2 times 5 plus 1, which equals 11. So a number is odd if it can be written as 2 times some integer plus 1. Now let's look at a proposition. Proposition 3. The sum of two consecutive integers is odd. And we have to prove that. So we'll start off with this. We start off with some number and we will use a as the variable. So we have a and the number after it will be a plus 1. The reason we choose a plus 1 is because we're looking for the sum of the two consecutive integers. To see this better, imagine that a was a number 2. The next number is 3, but it can be written as 2 plus 1. Notice they both have the number 2. This will be the number 2, and this is 3, just written as 2 plus 1. If we see this, we can see that this number can be written using the previous number. So 3 can be written as 2 plus 1. So we are using a because the proof is asking for any two consecutive integers. So now we have to add them. So we'll do a plus 1, which is the next consecutive number. In the proof, we're trying to show that the sum is odd. So a plus a1 is equal to 2a plus 1. By using the definition of odd, we see this is odd. Thus, the sum of two consecutive integers is odd. Note, definition of odd. An integer n is odd if n is equal to 2k plus 1 for some integer k. So this was the answer we got. And if we look back to the definition of odd, it's written as 2 times something, some integer, plus 1. And that's what we have here. Next, proposition 4. If n is even, prove that n squared is even. So here's a proof. So it says, if n is even, prove that n squared is even. So this part right here, n is even. We have to assume this part. So we start out by saying, assume n is even. And now we want to show n squared is even, because that's what we're trying to prove. Since n is even, by the definition of even, n can be written as is equal to 2k for some integer k. We want to show n squared is even, so we square n is equal to 2k. So now we have n, which is squared, is equal to 2k that's being squared. So this becomes n squared. This becomes 4k squared. Next, we write it, n squared is equal to, and we rewrite 4k squared as 2 times 2k squared. You'll see in a moment why we did this. Now, we let w equal 2k squared, which will be this part. The reason we do this is because 2k squared will be some integer. After we multiply 2 and k is squared, so we can write it as any integer. So we know this will just become some integer, 2 times k squared. That in the end will be some integer. I chose for it to be w. So Alright, n squared is equal to 2w. This step right here is important because it leads us to a definition we know. So this w could have just been any other letter. I just chose for it to be w. But the key thing we need to recognize from here is this will be just some integer. 2 times k squared will be just some integer, and I just chose for it to be w. The letter we choose doesn't really matter. So now we're left with n squared is equal to 2w. By the definition of even, we see this is even. Thus, if n is even, then n squared is even. So we're left with this. N squared is equal to 2w. And if you go back to the definition of even, is even if n is equal to 2 times k for some integer. So if we have it as 2 times some integer, that's even. And exactly what we have here, 2 times some integer. So now that we saw some proofs, we will go a little back just to understand why we do certain things in certain proofs. So what does it mean for a statement to be true? A statement is true when we have a given or assumed or hypothesis that implies a conclusion. The implies part has been through via definitions or previously shown statements. So things we know to be true. So an example. Example 1. 6 is even. This is true by definition of even. N is even if n is equal to 2k, where k is an integer. And that can be written as this, because 6 is even. So we can write it 6 is equal to 2 times k, where k is equal to 3. So by using definition of even, 6 is even. Now, what does it mean for a statement to be false? When we have a given or assumed or hypothesis, but we cannot come to a conclusion, meaning the conclusion does not always follow. So example 2. If n is even, then n over 2 is even. This is false. If n is equal to 10, although it is even, if we divide it by 2, we get 5. 10 over 2, we get 5. 5 is odd, not even. So for a statement to be false, as long as we find one exception to it, something that makes it false, then the whole statement will be false. Now, how to prove a true statement. A true statement will be something as if A, then B. So, in order to do this, we assume A and we want to show B. This is abbreviation of we want to show. So we have to break down what does A mean, what does B mean, and what definitions or theorems we have to use. So if we look back at proposition 4, it says, if n is even, prove that n squared is even. So we have to assume our A, and we want to show our B. So again, in proposition 4, if n is even, this is our A. N is even. So that's what we have to assume. That's what we did here. Assume n is even. And our B would be prove that n squared is even. That's what we did this part. We want to show n squared is even. Okay. We will now do another proposition, proposition 5. This one more trickier. So it says, if x and y are even, then x plus y is even. So here's our proof. We have to do the assume A and then show what our B, show what we want for B. So our assume part, A, would be this part. X and y are even. So assume x and y are even. We want to show x plus y is even. Since x is even, by the definition of even, it can be written as x is equal to 2k, or k some integer. I just use the definition. Since y is even, by a definition of even, it can be written as y is equal to 2m, where m is an integer. So I just use the definitions to get this. Note, I used k and m as an integer, and they are not the same letter because they have to be different. So I notice I put 2m and 2k. There's a different integer, different variable I use because they cannot be the same. they have to be different because they're different definitions. This is for x and this is for y, so they have to be different. So if you look back, we have to prove that x plus y is even. So now we have to add x plus y. X plus y is equal to 2k plus 2m. We can take out a 2, rewrite it as 2 times k plus m. And now we will do the same thing we did in the other step. Let k plus m equal n. The reason we can do this is because k plus m will be some integer, so we can write it as any integer, and I just chose for it to be m. So again, k plus m will be some integer. Once you add them, we'll just have one letter, one outcome. I just chose for this to be n. Again, choosing a letter doesn't really matter, but the important thing is to know why we did this. So I will let k plus m equal n, and we write it as 2 times n. So by definition of even, we see this is even. Thus, x plus y is even. Because based on definition, even is if only it can be written as 2 times some integer, and that's exactly what we have here. Okay, now we move on to a definition. Definition 3. An integer n divides m and can be written as n divides m. This right here means divide, where m is equal to nk, and k is an integer. In the same context, we may also write m is divisible by n. So n divides m is just written as this in math. Or it can also be written as m is equal to n times k, which is the integer. For example 3. 2 divides 6, because 6 is equal to 2 times 3. So this is the n, this will be our m. So if we look here, 6 is equal to 2 times 3, it's just written in this form. M is equal to nk. So we have m here, which is 6, is equal to 2, which will be our n here, and k in this case will be our 3. So again, it's seen here, m is equal to nk, m will be our 6, 6 is equal to 2 times k, this is our n, 6 divided by 2 equals k. Since we have an outcome of k, we know it does divide. In this case, k will be 3. Now we move on to proposition 7. Suppose n and a are integers. If n divides a, then n divides a squared. So here's our proof. Assume n and a are integers, and n divides a. We want to show n divides a squared. By definition 3, since n divides a, there exists some integer k such that a is equal to nk. So in order to get this, I just use definition 3 from up here, just this. So now we have this. So we need to show it for a squared. So we square both sides. So we have a squared is equal to n times k squared. Now we have n squared times k squared. And now we take out an n and have n times nk squared. Now we let nk squared equal to m. So the reason we can do this is because we are squaring k and multiplying it by n, so we know it will be some integer. I just chose for it to be m. So again, like other examples before, this in the end will be some integer. So I just chose for it to be m. So now we have a squared is equal to n times m. So by definition 3, n divides a squared with this. N divides a squared written as n divides a squared, or also written as a squared is equal to n times m, which is what we have. Thus, n divides a squared, because this is what we have right here. Okay, now we move on to a definition. Definition 3. An integer n divides m and can be written as n divides m. This right here means divide, where m is equal to nk, and k is an integer. In the same context, we may also write m is divisible by n. So n divides m It's just written as this in math. Or it can also be written as m is equal to n times k, which is the integer. For example 3. 2 divides 6 because 6 is equal to 2 times 3. So this is the n, this will be our m. So if we look here, 6 is equal to 2 times 3. It's just written in this form. M is equal to nk. So we have m here, which is 6, is equal to 2, which will be our n here, and k in this case will be our 3. So again, it's seen here, m is equal to nk. M will be our 6. 6 is equal to 2 times k. This is our n. 6 divided by 2 equals k. Since we have an outcome of k, we know it does divide. In this case, k will be 3. Now we will look at proposition 8. If x is even and y is odd, then x plus y is odd. So here's the proof. Assume x is even and y is odd. We want to show x plus y is odd. Since x is odd, by definition of odd, x will equal 2 times k, where k is an integer. Since y is odd, by definition of odd, y is equal to 2m plus 1, where m is an integer. So now we add them. X plus y will equal 2k plus 2m plus 1. We take out a 2. We can write that as 2 times k plus m plus 1. Now we let k plus m equal r, because we know k plus m will be some integer. So now we can write it as 2 times r plus 1. By definition of odd, this is odd. Thus, x plus y is odd, because the answer right here is written in the definition of odd. Now we will look at proposition 9. If x is even and y is odd, then x times y is even. So here's the proof. Assume x is even and y is odd. We want to show x times y is even. Since x is even, by definition of even, x will be equal to 2k, where k is an integer. Since y is odd, by definition of odd, y will equal 2 times r plus 1, where r is an integer. So now we multiply them. X times y will equal 2k times 2 times r plus 1. If we distribute the 2k, we will have 4k squared plus 2k. And now we can just take out a 2k. We'll have 2k times 2r plus 1. Now we let k times 2r plus 1 equal to t, because that will be just some integer. This will just become some integer. I let it be equal to t. So now we have 2 times t. By definition of even, this is even, because definition even will be just 2 times some integer, which we have here. Thus, x times y is even.